So let's talk about the variance of a random variable. Just like for the expected value, we distinguish between the case x is a continuous random variable and x is a discrete random variable. So let's begin by considering a discrete random variable. And let's say we have a simple setup. So x is a discrete random variable. It has a range consisting of n possible values. So it can take these values x1 through xn, for example 1 through 6. It has a given probability mass function f of x. That means that we know the probability that it will take each of these possible values. It has an expected value mu. So given these conditions, we define the variance of x from this formula. The sum, I go from 1 to n, xi minus mu squared times f of xi. So first thing we'll do is we'll look at how to calculate the variance in Excel using this formula and just a simple example, and then we'll have a look at this formula and we'll learn that the variance is a measure of spread in the possible values. So here's a simple example of a random variable. It can take 4 different values, 1 through 4, and this is our probability. So this is the probability mass function. So before we can compute the variance, we need to calculate the expected value. And the expected value is just the weighted average of these 4 numbers where we weigh by these probabilities. So we do x times p, calculate a2 times b2, copy this down, and then simply sum it to get the expected value. Well, actually, let's keep it down here. Here. So it's just the sum of these xi times pi. If we look at the formula, the thing we need is the deviations from the expected value. So we need to calculate xi minus mu for all the observations. So let's do that. X minus mu. And that will be the x value minus cell F9. So let's put a $sign on the 9 so it doesn't increase. So those are the deviations from the expected value. Now let's do the next part, and if you look at the formula, we see that in the next part we need to square these deviations. So let's do this x minus mu squared. So that's just simply this squared. So now we have that. And finally, to get the terms in the sum, we need to multiply these squares with the probabilities. So we need to weigh these squares. So we do one more. Let's call it x minus mu squared times the probability. So that's now this term, and to get the weights we multiply with the probability, copy down, and now we have the column we need to calculate the variance. So the variance is then simply the sum of these terms, the sum of these guys. So the variance for this particular random variable is 0.84. So to get some intuition about this formula, let's simplify things a little bit and let's make each possible outcome equally likely. Since we have 4 of them, we need to make each probability 0.25. Now, since they're equally likely, the expected value is just the average of these. It's typically the weighted average, but the weights are the same, so the average is 2.5. So that's the expected value, right in the middle. If we look at the deviations from the mean, from 2.5, these two observations, 2 and 3, are a half a unit away from the mean, while these two, 1 and 4, are a little bit further from the mean, 1.5 units. So square that, then these two gets a pretty large number, while these two, we have a pretty small number. And the variance is now, since each outcome is equally likely, simply the average of these. 225 plus 0.25 is 2.5, so it's exactly half of 2.5. That is 1.25. So in this particular case, when the outcomes are equally likely, the variance is simply the average of the square deviations from the mean. That means that if the deviations from the mean are on average large, the variance is large, and vice versa. So the smallest value we can get for the variance, we try to keep the expected value at 2.5. If each outcome had been 2.5, then clearly the deviation from the mean is 0 squared 0, and in that case the variance is 0. So in this case, each possible outcome is the same. That means that this random variable can only take value 2.5 with certainty, and then it has no variance. If we increase these a little bit, so we go, this one is just 0.1 unit away from the expected value, and let's say this is 0.2 units. 0.1 in the other direction and 0.2 units. We keep the expected value at 2.5. Now the deviations from the mean is a little bit larger, so the average square deviation is now a little bit larger, 0.025. And the larger we make these deviations from the mean, the larger will be the variance. So we take this back to 1, 2, 3, 4. It has increased to 1.25, but we can make it even larger. We can take the deviations for these two to 1.5 units. So we can take that to 1 and 4, and then we can take these to 0 and 5. Same expected value, larger deviations from the mean, and a larger variance, which is now 4.25. The final thing you need to notice about the variance is that it is not simply the average of these square deviations. This weight comes in, plays a role as well. So outcome which has a large probability, they will play a much bigger role in determining the variance than has outcome which has only a very small probability. We can see that in a similar experiment. So if we take these back to 1, 2, 3, and 4, where the variance is 2.5, if I change the probabilities such that these two observations have a higher probability, remembering they have a smaller deviation from the mean, then the variance will go down. So if I change, let's say, these probabilities to 0.4 and 0.4, and I change these guys to just 0.1 and 0.1, then the variance goes down to 0.65. And the opposite is of course true. If I put a bigger weight on the on the values where the deviation is large, then we get a much larger variance, 1.85 in this case. So the weighted average of the square deviations from the mean, that's what the variance is. If we go to a continuous random variable where the random variable can take an infinite number of values in an interval, then clearly the sum will not work. So the sum is replaced by an integral. So if I have a continuous random variable, and let's say now I have a range which is from A to B, and I have a probability density function, in this case PDF. I have calculated the expected value. Then the formula for the variance is very similar, replacing the sum with an integral. So we integrate square deviations from the expected value, and we weigh it with the probability density function. So that means that you can still think of the variance as the weighted average of the square deviations from the mean. For a continuous random variable, we can visualize the variance using the PDF. This is the PDF of the standard normal. The weighted average, or the expected value, is 0 because of the symmetry. So mu is 0. And for the standard normal, if you square the deviations from the mean, which is just the x value, since the mean is 0, so you have 0, 1, 4 and so on, and you weigh that with this probability density function, you can show by calculating the integral with this function that it has a variance which is 1. There isn't really any way of seeing directly from the PDF that the variance is 1. Like there is, we can immediately see from the PDF that the expected value is 0, as this 0 point here would be the center of gravity of this graph. However, if you put two probability density functions in the same diagram, you can typically see which one has the highest variance. This one is the PDF of the standard normal, so this has the variance of 1. If we look at the navy blue PDF, we see that this random variable has a smaller probability of returning a value close to 0. For example, if we look at the probability of getting a number between -1/2 and 1/2, it would be something like this area for the blue guy, while it would be this area for the red guy. So that's larger. To compensate for that, it has a higher probability of returning a number further from 0. So let's say the probability of getting a number between -2 and 3 is this area for the red guy, and it's this area for the blue guy. Since we're taking the weighted average of the square deviations from the mean, the blue one has bigger weights on these guys that are far from the mean, and therefore it will have a larger variance. Actually, the way I've drawn this one is that it has a variance of 2. Similarly, a even skinnier graph would then be taller, like that, and that would have an lower variance. So this would have a variance which would be less than 1. So in general, the skinnier and taller the PDF is, the lower the variance. The thicker and shorter the PDF is, the higher is the variance. Alright, so we have the definition for the discrete and the continuous, but they have the same interpretation. It's a measure of the spread in the possible outcome. More exactly, it's the weighted average of the square deviation from the mean, where we weigh with the probability mass function in the discrete case and the probability density function in the continuous case. So a couple of things to notice about the variance. First of all, it can never be negative. We are weighing the square deviations, and weighted average of numbers that are never negative cannot be negative. The smallest value it can take is 0. We view that as the case that there is no variance in the random variable, and that happens only in one particular case. It happens in the case when the random variable can take only one value. If it can take only one value, say 5, then the expected value of the random variable is that same number 5. So the square deviation is 0, weighted that with 100% and you get 0. But as soon as the random variable can take two values that are different from each other, each with a positive probability, both of the square deviations will be non-zero and the variance will be positive. It's very important, and unfortunately a big problem for many to learn probability theory and statistics, to distinguish between the variance and the sample variance. And typically, I guess the root of the problem is that the sample variance is by many authors just called the variance. So many authors uses the terminology variance when they actually mean the sample variance. This tends to cause a lot of confusion further ahead, so I would really recommend you to be very careful with the notation here. So remember, the variance, that's a property of a random variable. We need the probability density function or the probability mass function to find the variance, but it is a property of a random variable. The sample variance, on the other hand, is a property of a sample. If I have a sample of n observations, I can calculate my sample variance. They are also calculated differently, although both of them considers deviations from the mean. The variance considers deviations from the expected value, while the sample variance considers the deviations from the sample mean. Also, for the variance, it's the weighted average of these deviations, weighted by the PDF or the PMF. The sample variance, there is no such weighing process. Each sample has the same weight. And if you continue to study statistics, you'll see that in certain cases, with certain assumptions, the sample variance may be what's called an estimator of the variance. If I don't know the variance of a random variable, but I have a sample, then I can calculate the sample variance, and that's going to be an estimate of the variance. It's also very common to consider the square root of the variance, which we can do because it's never negative. And the square root of the variance is called the standard deviation. So it's defined like this. Common notation SD of x, standard deviation of x, is the square root of the variance. Also, the most common symbol for the variance is sigma square. For some reason, the Greek symbol sigma has been associated with variance. With this notation, we typically then use sigma for the standard deviation. Well, simply because the square root of sigma squared is sigma. Notation-wise, it's very common to denote the sample variance with S square, and then the true variance or the variance with the symbol sigma square. And there is a reason for that, and the reason is simply that the variance of a random variable is typically unknown. And it's not uncommon to use Greek characters for things that are unknown in probability theory, statistics, and econometrics. And to use the corresponding Roman character, which is s squared, for the estimate of the variance.